Hello, my name is Thomas Dimitrovich. This session will focus on selectively coordinating circuit breakers around a transformer. The example that we'll use is a 30 kVA transformer with a 480 volt line-to-line primary voltage and a 208 volt line-to-line secondary voltage. We will select all of the circuit breakers that you see here to properly protect this 30 kVA transformer and achieve a selectively coordinated system. The first step is to calculate the primary and secondary full load amps of the transformer and use that information to determine the maximum circuit breaker sizes on the primary and secondary mains for this transformer per National Electrical Code requirements. The primary full load amps is calculated here as 36.08 amps at 480 volts. The secondary full load amps is calculated as 83.27 amps at 208 volts. We use Table 450.3b out of the National Electrical Code to determine the maximum circuit breaker sizes for primary and secondary mains. We arrive upon the maximum size of the primary overcurrent protected device by multiplying 36.08 amps by 2.5 and we get 90 amps. We get to the maximum size main overcurrent protective device by multiplying 83.27 amps by 1.25 and we get 104 amps. Now, we can't purchase a 104 amp circuit breaker, so we're permitted by the NEC to go to the next higher standard overcurrent protected device size, which is a 110 amp circuit breaker. The standard overcurrent protected device sizes can be found in Article 240 of the National Electrical Code. In NEC 2017, our reference is Table 240.6a. This gives us the standard ampere ratings for fuses and inverse time circuit breakers. The next calculation we need to make is the short circuit current on the secondary of this transformer. We'll put our math together and calculate the infinite bus short circuit current on the secondary of this transformer. Per the equations that you see here, our current is 2082 amps. Remember, this is based on a 30 kVA transformer with 4% impedance. If you change those two parameters, the numbers will be different. 2082 amps is the number that we'll selectively coordinate to for this example. But keep in mind, too, we're omitting some impedances that may change the short circuit current on the secondary. We're using the worst case impedance transformer, which is the lowest impedance that we can get from a manufacturer. We're also omitting the secondary conductors that connect the main overcurrent protective device with the transformer. This could reduce the available fault current at the secondary of the panel. We're also omitting the fact that we will not have an infinite bus on the primary. We'll probably be starting with some lower level of short circuit current at the primary of the transformer. These omissions may, in reality, be insignificant to the process we'll be following. The bigger impact will be if our actual transformer shipped and installed has an impedance greater than that which we used in our calculations. That's the more significant impedance in this situation. We're approaching this as the worst case scenario, as we don't want to have to make changes after the fact. We don't want to see as-built drawings come in with impedances of transformers lower than what we anticipated, or conductor runs that are less in length than what we anticipated, because that will increase the short circuit currents. We take this as a worst case scenario to minimize our exposure and risk. First, we'll focus on the secondary of the transformer and select the main and branch devices in this panel board. The largest circuit breaker in the panel board branch locations, circuit breakers B1 through B4, is a 20 amp device. We're going to use the Eaton's BAB20 as the device in that location. Because we have 2082 amps available fault current on the secondary of the transformer, we have to select a main circuit breaker for this panel that selectively coordinates with that BAB20 up to 2082 amps. Remember that the main device cannot have an amp rating greater than 110 amps per the National Electrical Code. Our analysis will take us to the circuit breaker selective coordination tables to identify what breaker pairs selectively coordinate for currents up to 2082 amps and do not have a minimum long-time pickup of greater than 110 amps, the maximum size that the NEC tells us we can have for this application. This is the circuit breaker selective coordination table, which tells us to what level each circuit breaker pair selectively coordinates to. Across the top, you have the upstream circuit breaker, and down the left-hand side, we have the downstream circuit breakers. The minimum trip is going to be an important parameter, as it cannot be greater than 110 amps. Here I have eliminated those upstream circuit breaker options where they cannot be adjusted to or below the 110 amp maximum that the National Electrical Code tells us we can use. I have 4 possible viable solutions. To begin the selection process, I start with the BAB20 on the left-hand side of this spreadsheet, and that has to selectively coordinate up to 2082 amps. To select the proper upstream device, I move to the right in this table until I find a device that is capable of achieving my protection of 110 amps and has a number in the table that exceeds or equals 2082 amps. The first possible device I come to is the F-frame 100 amp thermomagnetic circuit breaker. This pair selectively coordinates up to 1000 amps, which is not greater than or equal to 2082 amps. This pair is not adequate. The next device I come to is the 160 amp frame F-frame circuit breaker with an electronic trip unit that can be adjusted down to 16 amps. This pair of devices will selectively coordinate up to 600 amps. This too is not adequate. The next device is the 160 amp frame circuit breaker that can be adjusted down to 60 amps. This pair selectively coordinates up to 1200 amps. Again, not adequate. Finally, we get to the 225 amp frame F-frame circuit breaker with an electronic trip unit that can be adjusted down to 100 amps. They selectively coordinate to 2300 amps, which is greater than 2082 amps. This pair will work. Now we have the downstream panel board circuit breaker solutions selected. We have the branch circuit breaker as a BAB20 and the main, which is an FDE circuit breaker with a 225 amp frame and a 100 amp trip. We've achieved selective coordination up to 2300 amps. So now we're going to focus on the primary circuit breaker B6. We will go through a very similar process with a twist that is unique to transformer applications. For a short circuit on the secondary of this transformer, the primary circuit breaker will see a smaller current based upon the turns ratio of the transformer. To calculate that current, I multiply 2082 secondary amps by 208 secondary volts divided by 408 primary volts. This shows us that for a 2082 amps calculated short circuit current on the secondary of this transformer, the primary current flowing during that fault will only be 902.2 amps. For our sake, we're going to use 903 amps. To select the primary circuit breaker that selectively coordinates with the secondary BAB20, I use the selective coordination tables as before, but I use 903 amps as my starting point to determine selectivity of circuit breaker B1 with circuit breaker B6. We will use the circuit breaker tables to select our upstream circuit breaker. I cannot have a minimum trip that exceeds the NEC maximum of 90 amps. I've crossed out the circuit breakers at the top of this slide that cannot be adjusted to or below the 90 amp maximum required by the National Electrical Code for circuit breaker B6. These circuit breakers cannot be used on the line side of this transformer. I have two options available that can be adjusted to or below the NEC maximum. They're both F-frame circuit breakers and they're both electronic trip units. One has a 160 amp frame that can be adjusted to 60 amps and the other has a 60 amp frame that can be adjusted to 15 amps. We begin our selection process on the left side of this table with the downstream circuit breaker, which is the BAB20. This device has to selectively coordinate with the upstream device up to 903 amps. Again, we are going to move across the table and find a pair that selectively coordinates to a number greater than 903 amps. The first 80 amp F-frame circuit breaker selectively coordinates with the BAB20 up to 600 amps. This is not acceptable. It does not exceed 903 amps. The second circuit breaker is the 160 amp frame F-frame device with an electronic trip unit that can be adjusted down to 60 amps. This pair selectively coordinates up to 1200 amps, and it exceeds the 903 amps necessary, so it's a good selection. So now we've selected all of the circuit breakers around this transformer, and they will selectively coordinate for all short circuit current values as long as my 30 kVA transformer doesn't change to a different kVA, and as long as my percent impedance is not less than 4%. If my percent impedance is greater than 4% in the as-built phase, I may be able to select different circuit breakers around this transformer as the short circuit currents will be lower, and I may be able to use smaller circuit breakers or devices that are thermomagnetic only without the electronic trip units. Before I move on, I want to explore a little more of this application and talk about leveraging the time current characteristic curves. The engineer should understand that running to the circuit breaker selective coordination tables may not be a good first and only approach to selective coordination. An understanding of short circuit currents and an analysis of the time current characteristic curves may yield a more economical solution. It takes a little more effort, but could pay dividends in our solution. Let's select the primary circuit breaker of this transformer in this example using time current characteristic curves and a 903 amps of reflected primary short circuit current and see what we learn. This is the trip curve for the FD90 circuit breaker. It's a thermomagnetic circuit breaker and not the device with an electronic trip unit. Our focus will be on the instantaneous. As you can see, Eaton published this curve showing what occurs below 0.01 seconds. You may not see this in coordination software applications, as usually the curves are cut off at 0.01 seconds. The manufacturer's curves in many cases provide more information. What we see here is, for the 903 amps that the primary circuit breaker will see, the trip curve tells us that this FD90 circuit breaker begins to open at 0.009 seconds. We will need this data point as we look at the clearing time of the downstream BAB20. If the clearing time of the BAB20 is faster than 0.009 seconds at that secondary short circuit current, these devices will selectively coordinate. This is the trip curve for the BAB20. As you can see, the instantaneous pickup range for the 20 amp circuit breaker is from 200 amps to 400 amps. We are well into the instantaneous region for the 2082 amps of short circuit current on the secondary of the transformer that this BAB20 will see during that short circuit. The clearing time of this circuit breaker is 0.0085 seconds. That is less than the 0.009 seconds of the 90 amp F-frame thermomagnetic circuit breaker upstream. So the FD90 will selectively coordinate with the BAB20 in this application. What we did by walking through this time current characteristic curve analysis was remove an electronic trip unit from the upstream device and reduce the frame size, resulting in a more economical solution. This took a little bit more analysis and research, but it paid off. What we learned here is that we should consider the time current characteristic curves with an understanding of the short circuit currents before going to the tables. The smaller and faster that the line side circuit breaker B6 is, the better position we'll be in when we focus on selectively coordinating the devices up through to the utility. So to summarize our discussion, when selectively coordinating circuit breaker solutions, we're going to be dependent upon short circuit currents. We need to leverage the time current characteristic curves before we run to the tables, because that could yield a more economical solution. We're going to select the line side circuit breaker based upon the short circuit through fault current, not the fault current that's available on the secondary. And remember, use minimum impedances and short conductor lengths to avoid problems after the installation is in place. Fixing selective coordination issues after the design is done and installed can get expensive quick. Thank you for taking the time to talk about this technical topic.